Hello, welcome to this video. So in this video we're going to be talking about one of the rarely commented problems with string theory. Now string theory has quite a long history. String theory began as a way to understand the flux of gluons within nuclear matter. However, it kind of evolved and developed and started to become a candidate for a theory of everything upon a particular interpretation of a particular loud vibration that seemed to correspond to the expected properties of a particle you would obtain if you were to quantize general relativity, so a relativistic classical gravitational field. Now that's a very brief overview, and string theory has come under a lot of heavy fire and criticism due to a wide variety of factors, including the lack of observations of ideas that many string theorists have faith in, such as the lack of observation of supersymmetry. But this video is really talking about a more fundamental problem, which string theory, having a lot of funding but very little experimental success, has fallen prey to. So, this idea is that string theory is essentially too smart for its own good, and has become a loosely connected scattering of clever and technical ideas which have very little coherent structure. And I'll expand on that during this video. Now, it's worth making at the start a couple of points very clear. Firstly, string theory is incredibly technical. Have I looked at some of the maths of string theory? Yes. Do I understand some of the ingredients that goes into string theory? Yes. But am I an expert in string theory? No. There are very significant gaps in my knowledge. That's a first caveat to make. The second caveat is that it is incredibly hot today. So if there are technical difficulties, and due to being hot is one of the reasons why camera equipment may not work too well, so it's just my voice over. I do apologise for my lack of video presence, but hopefully my voice will do given the technical limitations, particularly bearing in mind how warm it is of late. So, to understand the issue with string theory, I need to talk about what makes so many other areas of physics, particularly the well-established areas of physics, so successful, and then we can compare this to string theory. So, the other areas, particularly classical mechanics, statistical physics, quantum physics, relativity, quantum field theory, all these different areas have independent, self-consistent, clear guides for how quantities and equations relate to each other. There is a clear story they are telling. There are clear dialogues going on within the mathematics, how everything ties together, how to interpret things is clearly laid out. Now, sometimes there are various physical interpretations you can give to mathematical processes. This is particularly the case in quantum physics, and also, although less often spoken about, it is also the case in relativity. So there might be various philosophical approaches you can take, but there are clear philosophical, consistent pictures that allow you to understand the physics of what's going on, and accompanying these are well-connected mathematical constructs and sets of equations, which package everything together in a really neat and tidy way. And this is actually so important, this idea of packaging information into a coherent narrative, that this narrative, independent of the area of study, is called, well, it has its own name, it's called a framework. Now, a framework consists of a wide variety of things, and I've just tried to summarise some of the things frameworks traditionally have here. This is not like irrefutable. This is just my summary of a framework. So a framework contains a set of axioms, or, in other words, a set of assumptions. And you need these assumptions, because if you don't make any assumptions about a physical system, you won't be able to state anything meaningful about the physical system. We have to start with some premise for what the system might be, or what kind of dynamics are reasonable for the system. Now, it's worth saying these assumptions vary drastically between different frameworks, because different frameworks encapsulate different areas of physics. For example, in classical mechanics, we presume that a particle undertakes a single trajectory, and that is an axiom, that when a particle is moving, that movement can be described through a single trajectory. Now, that idea doesn't fit within some philosophical approaches of quantum mechanics. So, the axioms can vary between different fields of physics. But once you've got, for a particular framework, a set of axioms, the framework will often then start to describe precise mathematical nomenclature relating to the physical quantities. So it will start to introduce technical terms. That could be things like the idea of a charge, be that electric charge, colour charge, nether charge, lots of different types of charges you could be talking about. Potentially, if we're looking at magnetic monopoles, you might even talk about magnetic charges. And it will describe what these things are, give some symbols, and perhaps say what type of mathematical variable these things might be. Like, is it a scalar? Is it a vector? Is it a higher order tensor? Is it something that is reference frame dependent? All of these things will be described within the framework. And then once you've got your axioms, so you know what you are allowed to assume about the system, and you have defined your system clearly enough, i.e. you have precise mathematical nomenclature relating to the physical properties of the system, you then, within the framework, will generally have a set of very general equations. And by very general equations, I mean they do not refer to a particular system, they refer to a kind of system, a type of system. So it might be, for example, a system consisting of free particles. Or it might be a system where the perturbations about a particle's fixed position is small. For example, when describing the movement of phonons through a solid. So these equations are very, very general. They are not specific to a particular substantiation, if you like, of that framework through a particular physical system. And then lastly, the framework will consist of various metaphysical descriptions of what the equations physically describe. Now, in classical physics, this is still present. It is worth saying that the need for metaphysical descriptions is somewhat diluted because we are all intuitively familiar with classical physics processes, so we generally are not desperately needing to add some metaphysical understanding of what the mass is trying to tell us, particularly what the equations of motions or the dynamics is trying to say. When it comes to other areas of physics, like quantum mechanics, relativity, having a metaphysical interpretation, and often various metaphysical interpretations, is very helpful. It allows us to get a logical picture for what the framework is actually saying about our universal physical reality. It takes the abstraction covered in the first few parts of the framework and translates that into something physical, translates that into something relating to very tactile things, although I would use the word tactile very loosely, but as tactile as you can get. So, most areas of physics have frameworks. And a framework is critical because ultimately what all of these things correspond to is that you understand the physics. Understanding the physics often boils down to having at least some working knowledge of all of these things. With any of them missing, it's questionable to what degree you understand it. Now, mathematicians and mathematical physicists might just be interested in the top 3 bullet points, but within physics we do have to pay attention to the fourth one because we do want to describe our physical universe. So, this is the importance of a framework, and to quickly demonstrate how useful a framework is, I'm going to give an example of things that are very mysterious in classical physics without a framework, and how they become clear through a framework, before talking about the major issues string theory faces in relation to constructing a framework for string theory. So let's consider an example with ideas from classical physics. So, classical physics, as it is often introduced within schools and sixth forms, present some really odd symmetries that don't seem to have any explanation. Because, without a framework, it's odd why these things should be true or related. So, firstly, one thing we could ask is, as using the notation of modern physics, the total energy is proportional to the linear velocity squared. It's also proportional to the momentum squared, so we might write something like that. Now, this equation here is kind of mirrored when we're talking about something rotating. So both when something is undergoing translational kinetic energy, that is moving from one location in space to another, and also when the object is rotating, there seems a fairly consistent pattern between kinetic energy and velocity. Why is this pattern the same in both cases? Can this pattern be generalized to other things? Does it, only relate to linear velocity and also rotational or angular velocity? And question 2 is, well, why do particles which are not accelerating move in a straight line? I mean, some people might answer, well, it's due to Newton's second law, F equals ma, and then you can go, well, a free particle by definition isn't experiencing the resultant force, so that's equal 0, which implies that the acceleration is equal to 0, and as acceleration is changing velocity over time, we get that the change in velocity is 0. Thus, the particle has to move in a straight line. However, the problem with this reasoning is Newton's second law assumes, to begin with, that force has some intricate relationship with acceleration. You could ask, why is this the case? Particularly when you start to consider that light waves, which are a totally different thing to what Newton's laws seem to be describing, and that is because for something to obey Newton's laws, in a way that, the laws constrain the thing, our thing has to have mass. And an electromagnetic wave doesn't have any classical mass to speak of. So why do classical light waves seem to move in straight lines just like free particles? Even though classical light waves don't have mass, and therefore we can't really use Newton's law to suggest that they should move in straight lines. Like, how does light know to act like a free particle despite not being constrained by the notion of classical mass? And these are fairly significant mysteries. And we can kind of like resolve them. At least if we start considering the framework that we are working with. So, in terms of the framework, for question 1, the relationship between energy and velocity, well, if we look at something called Hamilton's equations, then there is no mystery occurring. And that's because Hamilton's equations don't specify whether we're dealing with translational kinetic energy or whether we're dealing with rotational kinetic energy or what type of velocity we're dealing with. we just go, well, we're going to deal with generalised position, generalised momentum, and write equations relating the evolution of generalised position to generalised momentum. We end up with a pair of coupled first-order partial differential equations called Hamilton's equations, and Hamilton's equations apply equally to objects undergoing translational motion as they do to objects undergoing rotational motion. So the fact that the guiding equations within the framework are not E equals half mv squared, but are something much deeper, the fact that the guiding equations deal with generalised coordinates means that actually there's no mystery regarding question 1. We should actually expect the symmetry which question 1 is pondering. And regarding question 2, we obtain the motion for either particles or, and this is a crucial bit, classical fields such as the electromagnetic field through Hamilton's principle of least action. And this applies, as I said, equally to free particles as it does to electromagnetic waves, and therefore there is no mystery regarding the symmetry questioned within question 2. So within the general framework, it's explicitly clear what's happening and why certain things at a less deep level are connected. It's very evident where that connection actually arises. So with a kind of like framework, we stop dealing with lots of noise, even if the noise is correct, and we start having a crystal clear understanding of the core dynamics and principles at play. And I'm going to build on this in the next slide and emphasise the importance, the vital importance of a framework, which will help us understand why string theory is deep in the weeds. So a framework allows progress. So firstly, it allows you to build larger theories. If you understand a framework and the assumptions that framework makes, and the technicalities present in the mathematical nomenclature, then you know what you might need to alter, what you might need to change, what you might need to adapt when some of those assumptions are no longer valid. You see, without a framework, if you want to describe physics where certain ideas that you've trusted before are invalid, well, without a framework, you don't know how to proceed, because without a framework, you don't understand the physics that you're dealing with well enough to understand how it should change or adapt when certain assumptions present within the physics break apart. And this is really, really perfectly emphasised when learning quantum field theory. Quantum field theory takes classical fields and applies assumptions that are allowed in quantum mechanics to those fields, and in the process gets rid of a few classical assumptions that you make within the framework of classical field theory. And so to understand quantum field theory, you need to have the framework of classical field theory so you know how to amend it to facilitate for these new quantum ideas. You also have to have a good enough understanding of the framework of quantum mechanics to understand how those ideas might become manifest when dealing with fields rather than particles. So, a framework is vital when you are going beyond um, what that framework is designed to deal with. Without a framework, you are attempting to climb a ladder, but the ladder doesn't have any steps with which you can climb the ladder. And then there's another reason why a framework really helps with progress, and that's with philosophical assistance. So, a framework within physics has a metaphysical component. It is attempting to describe what is happening in our universe and bridge the gap between the abstract mathematics and actual experimental observations. So, a framework allows one to clearly understand what one is talking about, or at least to have ideas regarding precisely what one is talking about, and that helps you propose new experiments to further test the theory, or helps you identify where perhaps the theory is slightly incomplete and might need new axioms or further axioms, or where existing axioms may need to be somewhat amended. So the philosophical component of a framework cannot be underestimated. So this is why, a couple of reasons why frameworks are immensely helpful within physics. And when you don't have a framework, things can go rather wrong. And this brings us on to string theory. So, as I mentioned, string theory has a very varied history. One of the leading physicists within string theory is a fantastic mathematical physicist, and I use the term mathematical physicist very intentionally, called Ad Witten. Ad Witten is fantastic, wonderful, love him as a person. I have no issue with his research. However, Ad Witten, it is worth mentioning, he definitely won awards in mathematics, I believe. I could be wrong on this point, but I'm pretty sure he's even won the Fields Medal in mathematics, which is similar in some ways to the Nobel Prize that one might get in science. So, extremely gifted man. But the key thing is, he's won tons of awards within mathematics. And his work is incredibly mathematical and filled with loads of beautiful ideas from mathematics. But it relates to so many different types of space-time, so many different ideas, that his work, and string theory is in a similar place, is wonderful, but it is slightly chaotic in terms of not having a framework that it is building. Now, this is not a criticism of Ed Witten. An individual researcher cannot be expected, nor should they be expected, to build a framework. I'm just using his research as an example, almost a anthropocentric emergence of the problems faced within string theory. That string theory is loads of brilliant ideas, but with no framework, no clear framework. There are some assumptions that string theory makes. However, precisely what those assumptions are saying, and which of those assumptions are needed or not needed, I mean, string theory is not elegant in its entirety. It has elegant pieces of mathematics, but in its entirety, it is very discordant, would be a good way to describe it. So, string theory has had extensive research over 50 years. Some people say that the actual money going into string theory is too much. Now, it's worth saying string theory is a pursuit of theoretical physicists. Theoretical physics, particularly the foundations of physics, doesn't tend to use up that much money. Now, whether string theory has had an unfair proportion of money given to fundamental physics compared to other areas of fundamental physics is a different question. But string theory has had a lot of people spending a lot of time working on it, and what we have now is a humongous set of ideas and principles, and some of these ideas are very disconnected from the core principles, which the subject began with. Some ideas are very disconnected from what is meant to be the heart of string theory, the kind of ideas covered within at least an introductory course. And if you would like to learn string theory at an introductory level, although it's worth saying when I say introductory level, I mean upper undergraduate dash postgraduate, so not PhD, but this is still advanced stuff. But if you would like to learn at that kind of level, there are some good books out there. And the very early, the core stuff is in perhaps relatively good shape. It's when you start going deeper where things just start getting really, really messy. And so my biggest problem with string theory is that string theory as a whole has no clear framework. I don't think it's very clear what it would mean for string theory to be true. Beyond some disconnected equations, I don't think it would be clear. Now, to be absolutely clear at this point, yes, if string theory was true, there are certain equations that would be true. But there wouldn't be a framework as we currently understand string theory, or at least we wouldn't have a framework just with those equations. In much the same way that, these two equations from classical mechanics, these two, if you can see them on the screen, hopefully it's recording what I write on the screen, but if not, I've got the equation for the kinetic energy of a free particle and the Newton's second law. These two equations, whilst within classical physics, don't really tell you much about the framework. You just have seemingly disconnected equations, or fairly disconnected anyway. And if string theory turned out to be true, we would be in a similar position in regards to understanding string theory. We would have a set of equations, like the Polyakov action, if I'm pronouncing that correctly, but we wouldn't have a clear framework as to what precisely string theory is trying to say. So, this is my overview of why I think string theory is in very muddy, deep waters. Now, this could change with time. I personally don't have a huge investment with whether string theory turns out to be true or not, but I do have an investment in making physics coherent and clear, and therefore the coherency or lack of coherency within a particular area of well-researched physics, such as string theory, is of a concern to me. Not great concern, I'm not going to lose sleep, but it is something that's worth doing a video on. But anyway, now, as I say, worth mentioning, take everything I say, as always, with pinches of salt. I am merely an intrepid explorer of the cosmos. Um, um, that's essentially all I am. And, be cool to hear your views, and particularly if anybody is learning string theory currently or researching it. It'd be great to hear what you have to say on these points, or any other points you would like to bring up regarding string theory. But anyway, I wish you a really good weekend ahead. I hope you enjoy the sun as much as you can enjoy it, I think. And the coming few days, it's going to reach 30 degrees, which might be a bit too warm, but I wish you a brilliant time and look forward to sharing with you some wonderful physics soon.